All right. Is my screen visible?
Yes, sir.
All right. So the last class we were talking about the modeling of the system with the how the total complete equations of motion comes up. And I've been trying to set up my own, for the KCS vessel, I'm trying to set up a good enough hydrodynamic modeling or dynamic model for our craft. So which will be one of your assignments. So you can hope to see some of that coming into light this week. Okay, so something should be posted on MATLAB Grader this week for you to try out and develop the KCS hulls complete modeling of the dynamic equations of motion. We'll try to take a first principles approach there. We will not be looking at a hydrodynamic derivative approach because we have not done experiments as yet on our craft in order to determine them. So we don't know them precisely. We can only get those values from other experiments which others have done. But for now, we will try to create our modeling based on first principles approach using the nonlinear damping and surge and the cross flow drag principles. All right, so that is on the assignment front. You should see something come up this week. I'll also be interested in creating a similar module in the Ross and gazebo framework as well. So that is definitely something I would be interested in trying to see my own hands based on what Aditya and Vallabh have come up with the basic framework of in the Ross. We'll try to kind of develop that and bring that elements into this architecture. Okay, so that in the absence of the experimental model being there, we can use our simulated model from the gazebo as a simulation environment on which we can test our things using ROS applications. But that is not strictly part of the course. So that's why we'll also be having a similar parallel running on the MATLAB Grader, where we can start seeing the same dynamics being programmed in MATLAB Grader. At an endpoint, we would like to see how this can convert into a real platform and can port there. I hope to kind of cover a little bit of it at least towards the end of the course, where we will look at how our MATLAB code can be ported to ROS. Similarly, how our existing code, which we are developing in Gazebo, we can bring all of that into a sort of a tutorial session towards the end of our course. That will be the plan. Okay. With that in mind, let's continue today talking about the guidance systems. So in any typical control system approach, you generally have three things. One is called guidance, the next is called navigation, and the last one is called the control. It's usually a combination of these three things which determines how the vehicle is performing or is it doing what we are asking it to do. And each of these three different things, three different systems have their own specific requirements or own specific purposes. So the guidance system's purpose mainly is that it wants to guide the path of an object towards a given point, whether that point be fixed or it may be moving in nature. But the idea is we have a craft which we want to go to a certain location, let's say. How do I make it go there? What are the feasible trajectories to get to that point? These are the things which we are discussing in a guidance system. Within the so-called guidance systems approach, there are a couple of things which we will talk about. So different motion control scenarios require different type of guidance per se, and we'll look at what those different types of guidances are. So the first is called a set point regulation or point stabilization, which means that I here only am interested in asking my craft to have a specified position and an attitude, which means I may say that in a dynamic positioning operation, I want my ship to be at a so and so latitude and a longitude and oriented with its heading angle at a so and so angle to the north direction, let's say. So that would represent what would be called as a set point tracking. So now I may have disturbances in terms of ocean winds, waves, and currents coming into the picture. And even with these disturbances, I want to make sure that my craft stays there, right? So from the guidance perspective, it's pretty simple that there's a latitude, there's a longitude, and a direction. That's all has to be tracked, right? So there is no really trajectory or things like that are not coming into the picture here. So this is the simplest of the guidance systems where I have a fixed point that I want to track, or it's a part of my state space, which I'm specifying as the input, saying this is my desired value that I want to hold. And then I'm trying to design a controller so that that can be held properly. So in this sense, there's nothing much going on here in terms of guidance. It's one of the simplest ways to go about providing a guidance. The second aspect is the more interesting one, which is called trajectory tracking. Okay, here what we want to do is we want to force the system output, which means we want to kind of look at our plant's output, which is its velocities and positions, and I want to force them to be following some desired path. Okay, I have a desired velocity and a position to be followed with respect to time, and I am kind of forcing my system to follow that particular predefined path. So this is where trajectory tracking comes into the picture. Notice here that in a trajectory tracking, time is an important aspect. So it's not just specifying this is the path that I want to follow, but I'm also saying at time t1 you should be here, at time t2 you should be here, at time t3 you should be there. So the objective is no longer saying that a set point, but now that set point is a moving, and it's moving with time in a prescribed manner. Okay, all right. So generally for such sort of trajectory tracking, we need reference models, because when we want to track a trajectory, first of all, we have to ensure whether the trajectory is actually trackable, whether the dynamics of our craft supports it, that such a trajectory can actually be tracked. There's no point in trying to track a trajectory which cannot be tracked by our craft. So for example, if I took a ship and I said that you start from 0 speed and then you suddenly execute a maneuver like this and go forward, I can't execute a maneuver sideways. It's simply not possible because the ship does not have a mechanism with which it can translate in this way direction, right? So if I give it a trajectory like that, such a trajectory cannot be tracked. So whenever we are doing a trajectory tracking algorithm, the guidance system has a greater role to play, in the sense that it should come out and give a proper trajectory which is consistent with the dynamics of the craft. I should not expect my craft to follow a path which it cannot follow. Physically impossible to follow. Such paths should not be coming into the picture. So this is why generally you will need what are called as reference models. So what I mean by reference model is, in the strictest of the sense, it says that let's say I have a craft that I want to track, let's say the KCS. I say I build a good enough detailed model of my KCS and simply use it to simulate a trajectory, and that becomes my so-called desired path. When I do the simulation, I know for sure that it has taken into account the dynamics of the craft into finding the path. So the path which I have generated through the simulation is more likely to be closer to a path that can actually be followed. Is that making sense? I'm not right now talking about how to get that desired path. I'm just saying that suppose I use the simulation model of the craft, which we developed so far, and I simulated it forward in time with some control inputs which I am giving, and it follows a path. That path is something which the craft can feasibly track. Right? Because the dynamics of the craft are more or less going to be similar. It may not be exactly similar. There's a possibility that when I actually do my experiment, My simulation model may differ slightly from my experiment, but still I'm at a much better starting point than giving it a very obscure path which it may not be able to follow. Right? So that is one way to do it, definitely, which is called the simulation of the craft using an adequate model of the craft. That's what you see. But then there are two other methods as well. And these are coming from the point of view of, I don't want to do a simulation because it is expensive. It takes time to do these things. It's computationally expensive. Can I get away with a simpler process? In which case, I may say that I would like to go with a low pass filter. So what a low pass filter is doing, whatever input I give, whatever is the low frequency component of that input, that is preserved, but whatever is the so-called high frequency component of that input will be removed, right? So suppose if I chose a joystick output, let's say a person is standing there and he is actually trying to do a joystick control. Okay, he's holding a joystick and then he's trying to move it around and wants to see how a craft responds. Kind of similar to what we were doing a couple of days ago in the wave basin, right? So here I want to kind of make sure that, let's say the operator is taking that so-called joystick which is looking at the speed, okay, and instead of you would typically expect a neat constant speed if you wanted to travel in a straight line. But when a human input is provided, it may not be as smooth, right? So you may actually see that this thing has significant vibrations around it. Correct? But it is the task of the guidance system to take that so-called joystick input, where a person is trying to control the craft using the joystick commands, and then convert them into a actual desired possible trajectory. So in which case, all those high frequency undulations are removed when I pass the signal through a low pass filter. And I get a more or less a straight line as an output if I really wanted to track a so-called straight line output. Now, joystick is just only one of the types of inputs which your guidance system can get. You can get an input from other sources as well, right? Some of the other sources might include weathers. What is the weather looking like? What are the environmental data looking like? They may also determine how your next desired trajectory should change. Okay, so suppose I have a set point regulation, then the joystick system definitely needs an input from the guidance system, definitely needs an input on the environmental parameters. Is everybody following me? Yes. So it's kind of sitting in between.
Sir,
Yeah,
I thought like this joystick is more on the control side, like we are giving it an input, the system an input.
correct. So typically you would like to think like that when we are doing in our wave basin, you would be right in thinking that it is actually more of a control aspect. But when you're actually doing a dynamic positioning in a large scale ship, right, your command doesn't directly result in a thruster command. Okay, because
Oh,
what you give as a joystick input might have to be translated into a desired trajectory first, and then a control system at the back of it kicks in order to track that so-called desired trajectory.
okay, okay. So in large scale, it creates a trajectory that
Correct.
joystick.
So in the large scale, you typically will have a decisive cascading of the way how it is going about. So let's say that in general, what will happen is in a dynamic positioning operation, it will not be completely autonomous. You'll always be having some person on board. So let's say I'm trying to transfer some weight from one ship to the other. Or let's say a supply vessel has come and I'm trying to take some equipment from it and put it onto my offshore structure.
Okay.
So there will be a person manning that vessel. There will be a person on the crane, and there will be a person on the offshore structure as well. And they will be trying to give a command that, okay, I need to now lift this up, or I need to increase my speed now. That command doesn't directly translate into the so-called control system. It first translates into a desired trajectory, and then beyond that, there is a control system which is sitting and saying, oh, okay, my desired trajectory has now changed. Now let me change my control thrusters so that I match the so-called desired trajectory.
Okay. Okay. Yes.
So I'm talking more here about the large-scale commercial applications rather than the small-scale boat. So if you are looking at our small-scale boat, you would be right that ideally that joystick is more like a controller, because what we have done in our craft here is I've taken the joystick commands and directly I'm adjusting the control voltage for the motors.
Okay. Yeah. Yeah.
Right? So when I move my joystick, what is happening? Actually, the control voltage to the motor is automatically changing. But in a real system, you would not have it in that manner, because then you can't isolate it to noises. So suppose I make a mistake somewhere here. I don't have a time for correction.
Yes.
Right? So in that sense, and then the amount of economic loss which you will see on those systems is much larger. So that sort of redundancy is very much required. Okay.
Yes.
So that is why in a typical DP operation, you will find that the joystick is a command which generally comes as an input into your guidance system rather than the control system directly. Okay. Very good question. It is different from what we are seeing in our wave base.
Yes, sir.
So the remote control that like when manually operating with the remote control, it will still do these fluctuations, right? So we are transmitting all those fluctuations also.
Right now we are, which
Okay.
means that even if you actually observed our actual craft, sometimes when our deadband, if it is not tuned very well, we may leave the joystick, but still the propeller will be slowly rotating with some speed.
Oh,
So these sort of things start to happen primarily because that there is a dead band and we are kind of slightly over the dead band. So the propeller actually is getting a signal as if, come on, keep rotating, although we have left the joystick completely. Right? But when we put this through a guidance system, then what happens? That translates first into a guidance algorithm where we can catch it. And then the control system need not be looking at this part of the problem at all. Okay. So it's kind of a cascaded environment. And there is a problem here that generally when we are talking about guidance, navigation, and control, it is one closed loop. Each one affects each other. So it's a chicken and an egg problem. Which one came first? You can't really precisely position it and say this one comes first, then comes that, and then comes this. They all three affect each other. But in a sense that when you're looking at DP operations, the guidance system is the one which is getting your keyboard inputs or this inputs. So if you haven't have watched, I don't know how many of you here have watched Titanic movie.
Yes, sir. I have watched it.
I keep coming back to that example. Have you ever looked at when they said the captain gives an order saying that let's go half ahead, okay? And then the guy actually takes the telephone and pulls down and talks to someone near the engine room, says
Yes.
half ahead, right? And then that fellow says, okay, half ahead, and people are now putting more coal into the engines to make it run. Right? So that is the manual version of the so-called guidance system. What we are seeing here is a more electronic version of it these days. Okay. Okay. All right. So in that sense, you may choose your reference models to be low-pass filters so that these undulations can be evened out at the guidance signal case, and you can pass the more viable inputs to your control system in order to do the tracking. The other method where you can find these reference models is through optimization methods. So sometimes you may say that it's not just a low pass filter that I want. I actually want to find a so-called optimal path. Or if I want to, let's say, minimize my fuel or maximize my endurance, So things like these might come into the picture, which you want to include into your guidance system. So I want to go from point A to point B, but necessarily using the lowest fuel consumption, and I have certain constraints like I can't travel sideways on my boat and I can only travel at certain speeds. My rudder is effective at different speeds in a different manner. How do I take all those constraints into account? A typical way would be to form an optimization problem around it with an objective function, try to minimize it, and then try to find a possible path for your path from point A to point B. Okay, now that is, as you would probably presume, sometimes can be cost intensive, or more so computationally cost intensive, right? So it may, for real-time applications, one would usually not want to have it in place because of the increased computational cost. From a real what you call real-time application standpoint, you would want to have a simple model which is computationally less expensive and can be implemented easily in real time. In such cases, low pass filters are the best way to go about it. Okay, but sometimes we may want to go for much higher value based methods where it is really important to conserve the endurance or conserve the fuel that we are consuming, in which cases we might be interested in an optimization problem or even a simulated problem. Okay, simulated problem will take care of the so-called constraints in our problem without me having to explicitly mention them. So in optimization problem, I have to specify the constraint that my ship cannot move sideways in some mathematical form. But if I'm using the simulation model of my craft, I need not do that. By nature of the simulation, it cannot do this sort of a trajectory anyway. Is everybody with me so far? Okay, excellent. So notice that whenever we are doing a trajectory tracking, we must account for both spatial and temporal constraints. So when I can't move sideways, that is a so-called a spatial constraint, or I can't move sideways immediately, is both a spatial as well as a temporal constraint. Because it's not that I really can't move sideways. I can always slowly turn my ship around and move that way. So my position of the ship can actually track a path like this. Are you understanding what I'm saying? So if I choose a point on the ship and I want that point to follow a path like this, it can technically do it by turning around, going this way, again stopping, turning around, and then going this way. But the point is that if I want to make it happen instantaneously, cannot make it happen. So I can't move this way suddenly, but I can always turn around and move this way. So the so-called constraint here is not a typical spatial constraint. It's not that I can't actually go sideways. I can't go sideways instantaneously. So it's a spatio-temporal constraint which is coming into the picture. Okay. This particular constraint is actually a non-holonomic constraint. For those of you who were there in that tutorial, which was being organized by Oceans 2022, you must have seen this. So these means that these can't be integrated to get a closed form expression. That's what it means. But it's not of relevance to us, so don't worry if you don't understand what that holonomic term means right now. Okay. Now, so that is what was called as trajectory tracking. So where we are actually expecting it to track some trajectory in time. So time is a part of the trajectory. The next one is called as a target tracking consideration. And in this case, the guidance system will have different functionality. In a target tracking case, we do not have any information on the path that is available to us. So it may look like something like, let's say the Coast Guard was patrolling and then they suddenly found a pirate vessel. Okay, now they start chasing the pirate vessel. What is the best way to intercept the pirate vessel? What is the best guidance path to be chosen or the desired trajectory to be chosen in order to catch the pirate vessel. We do not have any information on how the pirate is going to behave, right? We have absolutely no information. We only know its current state, that's all. We do not know how it's going to behave in the future. So there is no information on what path it is going to take. So that's why in target tracking considerations, there is no information about the path that is available to us. Similarly, there is no particular closedly defined trajectory which we can track. So nobody is telling us you move in a sine wave and that's how the pirate is going to move. Unlikely, right? They are going to try to evade us. So here the point is more so that the guidance algorithm should be able to take that into account, come up with a specific action of what is my desired trajectory, which satisfies this target tracking problem, and then the control system acts on that guidance provided by the guidance system. So that is a different style of a problem than what we saw in the trajectory tracking consideration. How do I deal with such problems? So this is where typically you see line of sight control or line of sight guidance or pure pursuit guidance, target bearing guidance. These are things which have evolved so-called from the missile industry. Okay, so when they wanted to, let's say, hit an aircraft, anti-aircraft missiles, you don't know how that aircraft is going to move, but you have to make a prediction on where it will be, and then you have to aim and hit. So things like these, where the information on the path or the trajectory is unavailable, how do I do guidance? Okay, the next one is called as path following. Okay, here what we mean is that we are following a predefined path that is independent of time. So in the trajectory tracking problem, I wanted it to follow a path in a specified time, and I wanted its location to be at a specified location at a particular time instant. At T1, I want it to be somewhere. At T2, I want it to be somewhere else. T3, I want it to be somewhere else. But I may also have a path following approach, which may be more relevant when I'm trying to do a survey operation, let's say. Let's say I want to take a port channel, look at it, and come back and determine where to dredge. Okay, typically port channels are dredged so that ships can come in without the risk of getting grounded. So I might want to survey from time to time just to find out where is the next dredging operation that I should undertake. Where is the material concentrated more? Where I need to put my dredge at work. In such cases, my target is to scour the entire map of the port. I'm really not interested in doing that in a less amount of time, but I'm more interested in getting a good bathymetry scan from my survey application. Right. So there, what's the path is not the trajectory is not the consideration. It's more so the path which is the consideration. So in such cases, I would be interested in path following problem, where the craft must follow a predefined path independent of the time. So there is no restriction on the temporal propagation along the path. It may go as slow as needed, it may track as fast as needed, but it has to follow the path that it has been provided with. And this is where you generally see methods like Dubin's path come into the picture, and we are going to discuss about this. It's a mechanism in which you can satisfy the constraints of the vehicle along with a sufficiently sharp enough turn that the vehicle can undertake this path. And it uses transcribing circles in order to generate these paths. So we'll look at how that is done. Okay, note that whenever we do a path following, spatial constraints like obstacles can be included in the path. So I may say that, yes, I'm trying to follow a path, but it should be free of obstacles. That is definitely a constraint which must be accounted for in a path following algorithm, but the time dependence is not accounted for. Whereas when we talk about a trajectory tracking, the time dependence must also be accounted for. Okay, so we'll start first with trajectory tracking, and then we'll kind of come back, slowly make our way back to the others, path following and uh, target tracking. So when we look at a trajectory tracking problem, let's say that I'm looking at a 3 degree of freedom system. My primary idea is I need to know what is my XY position of the craft, desired position of the craft, and what is the heading orientation which I need for the craft. So that is typically the 3x1 vector which I need to find. And we want to achieve this path, which means that I want to take the error between the actual value of my position minus the desired value of my position, and I want to drive this error to 0. As long as I can ensure that that error goes to 0, I can say that I'm going to be trying to following my desired path. All right. Now in this consideration, when I want to drive this error to 0, there can be different scenarios. I may have 3 or more controllers, which means I may have 3 or more thrusters in this case. Then the problem is called fully actuated or over actuated if I have more than 3. Okay, so if I have the number of control inputs that I am providing to the system are more than what the degrees of freedom that I want to control, such a system is called an over-actuated system. If the two are equal, it's called a fully actuated system. If it is less, then it's called a under-actuated system. So if I only have 2 controls and I want to do trajectory tracking, then that is a classic under-actuated problem. And typically you will find that most ships, okay, regular commercial ships fall under this so-called second category where they are under-actuated, because you can control only the speed of the propeller and you can control only the angle of the rudder, but you have to control 3 things when it comes to the desired trajectory: X, Y, and psi. So therefore it's a classic under-actuated problem. Okay, then another way where you can think of is sometimes I might want to have 2 controllers, 2 control inputs, and I want to do weather optimal heading, which means that the ship is aligned against the mean forces to wind, wave, and ocean currents. So I'm just trying to make sure that my vessel is oriented in such a way that it's having the least exposure to the wind, waves, and the currents. So my heading is not kind of always fixed, it changes with the environment. So I'm not holding my heading to be a precise value, but I am holding a position. I want to say that I want to be at so and so position, no matter what my heading is, depending on the environment. So such sort of a thing is called weather optimal heading, and you do a weather optimal control for such sort of scenarios. Then sometimes I may be looking at a 2 controls and a path following problem. As I said, let's say I want to survey the port channel, then this is what I'll be doing. I have 2 controls on the ship and I want to do a path following. Typically in such an approach, we can get away with doing the path following by reduction of the problem state, or the so-called configuration space, into 2D space. So instead of looking for a orientation as one of the key inputs, we are mostly looking at waypoints, and then I'm only interested in how much error there is along the track and across the track. So I can look at whether I am having an error, side track error, and whether I am having an along track error, which I need to compute. We'll look at this in more detail as we start discussing the math of it when we come around to it. So let me come back to this idea that for a trajectory generation, we need these reference models, which we talked about, and we talked about 3 major kinds. One are low pass filters, the other are called optimization methods, and the third one is using the simulation of the craft itself as a mechanism. So we'll focus today's effort mostly on the low pass filter based guidance. So what we are doing here is that so-called reference signal which is coming in, which can be either a joystick input or a keyboard input or a input which a system is defined taking base, it is kind of taking this action based on the environmental changes that it is observing. Those inputs are our reference signal R. That's what I'm referring to as R of t. Okay. And what I want to find out is the so-called desired trajectory or the desired states of my vehicle. How does this information, let's say the joystick information, translate into what is the desired X, Y, and Psi directions over time? Okay, so I am giving some joystick input that should relate to give me an actual value of X, Y, and Psi. That's it. How do I get those values? So those are the desired states, which are the output of the system. Is everybody with me so far? Yes, no?
Yes, sir.
Yes, okay, good. Now, this transfer function, when I take it in the Laplace domain, is the so-called low pass transfer function that I want to look at. So which means that if I were to look at a frequency dependent thing, so which means if I were to take S is equal to I omega, I can actually plot the magnitude of this low pass filter. Versus omega. Okay. Now this is not a typical controls course, but these sort of diagrams are what you would call as Bode plots. It's basically telling you, it's more like a response amplitude operator, right? You kind of see, you're more comfortable probably with the term RAO rather than with the term of Bode plots. But the idea is still the same. We are trying to look at what is happening to that so-called reference signal. So suppose if this filter looks more or less like, say, like this, what does that imply? And here I'm assuming that this is plotted in log scale, okay? So let's say log of this. What does that imply? If you look at a filter which looks like this in the frequency domain, what can you tell?
The magnitude is lesser for higher frequencies.
Correct. So which means, let's say now I have, so in one case, let's say R of t is given by this. And in the other case, let's say R of t is given by this. Okay. When I give these two inputs, when I give the first input to this filter, what will be my output? I'll even make this simpler by putting this as 0, let's say. So log of something is 0, which means that mod of thing is 1. What does that mean? When I give the left-hand side signal as an input to my filter, what will the output of that filter look like?
It will be the same.
It will be the same, right? Because the value of that mod of h is 1, so you should get back the same signal.
Yes.
But when I give the right hand side signal as the input to the same filter, what will happen?
That is a high frequency signal. So the filter, the value of log of that mod will be lower. And when we multiply that with this signal, it will go down to 0 maybe.
Correct. So its amplitudes decreases,
Yeah,
right?
it will
So when
decrease.
I get the output from these two things, I'll get back the same signal in this case, but the output from this second case may now start to look like this.
Yes.
Right? It kind of completely attenuates whatever is going on there. Is everybody with me here? Is everybody following me? Shadab, following me?
Yes, sir.
Anand?
The second graph I didn't understand.
Come again, Anand.
Sir, I didn't understand the second graph.
The second graph. This
Raise the equation.
second case, what is happening?
Yes.
This one is what you did not understand. Okay. So let's say that this fellow corresponds to frequency omega 1. Okay. So this period is 2 pi by omega 1. Okay. And let's say this fellow corresponds to frequency omega 2, which is here. Okay. So when I give the first fellow as an input to my filter, so the reference is given as an input, it gets multiplied by this low pass filter to get my output, isn't it? Yes.
Yes, sir.
So in one case, in this region, log of this thing is 0, which means this thing is equal to 1, right?
Yes, sir.
If this mod of HLP is 1 and I multiply that by I and it has mod equal to 1, I'm getting back the same amplitude, signal of the same amplitude, isn't it?
Yes.
Right? There may be a phase difference, which I have not spoken so far. But at least the amplitude of the signal itself will not change.
Yes, sir.
Whereas when I do it for omega 2, what will happen? Let's say that in this case, when I read off of the graph, this value is minus 10, let's say. What does that mean? If log is equal to minus 10, what does that mean? What does that tell me about mod of this fellow?
E power minus 1.
Yeah, assuming this is taking as e power. Otherwise, if I took it as log base 10, then it will be 10 power minus 10.
Yes, sir.
Right? So if its mod is now 10 power minus 10, and I multiply that with the original signal, what will happen?
Reduce.
It will reduce in its amplitude, isn't it?
Yes, sir.
So that's why the second graph, even though this is the input, the output looks like this.
Yes, sir.
Right? Because the amplitude has now suddenly reduced further. So what it is doing, this filter is basically saying that anything up till this frequency, let's say omega c, which we'll call as the so-called cutoff frequency, anything to the left of that, I will take it in and I'll pass it out just as is. And anything to the right side of it, I will attenuate. So any high frequency disturbances, I'll simply reject them. Is that making sense?
Yes, sir.
Yes. So that's what a low pass filter is essentially doing. So in this case, what it means is that as I was, let's say, giving the joystick commands, even if there is some unknowingly we are doing some extra high frequency variation, that will get attenuated when I'm looking at the so-called desired X, Y, and psi that I want to follow. Okay, and that's a good design. Why? If I wanted to follow all the small little variations in X, Y, and psi, my actuators will be working overtime. Right? And since my actuators will be working overtime, which means that my endurance will be less. So I can be at C for lower amount of time. Right? So in that sense, it is much more advantageous to actually have this sort of a system in place. Okay, all right. Let's continue further. So when we choose this filter, so this so-called filter that you saw here, right? Whenever I'm designing that filter, here mostly I'm playing with omega c as one of the values. And also I'll also see that not all filters can fall off so straight. So they may actually look something like that also. So how much is this overshoot value will also be something that you as a designer of a control system or a guidance system will be interested to control. You don't want to see too much of it come into picture. If the hump is too high, that means that there is a significant resonance occurring. There is very little damping in the system, which may cause more problems. So in that sense, you want to kind of make sure when you do the choice of your filter that this filter decently reflects the dynamics of your craft, which means whatever your craft could do in a low speed scenarios should be captured. At least all those frequencies must definitely be captured in that so-called low pass filter. It should be able to construct feasible trajectories. So the trajectory outputs that you provide in terms of X, Y, and psi, let us say, they should be something which the craft can potentially actually follow. Then you need to also account for, so notice that here we did not account for so far, but in a typical system, you need to make sure that physical speed and acceleration limits are accounted for, which means that you cannot accelerate suddenly. Those things have to be taken into account because the ship has a huge inertia. I may run my propeller now, but I may actually only start moving after a while. Right? So there is a gap between when I gave the actuation command to when I actually started moving. And that is happening because of the inertia of the vessel. So such limits on what is the maximum acceleration which is physically possible from your thrusters, what is the maximum velocities which are possible from your application of the thrusters. Similarly, what is the input saturation? Because sometimes I may want to give a very high input. So if you might have observed this on joysticks too. I may hold the joystick all the way over and it runs at a particular speed. I cannot go any more than that. It's fixed at that value, right? Even if I wanted to go faster than that, I can't. There's a saturation limit on it. So such saturation limits should also be taken into account when you're looking into the dynamics of it. Now, how do I do all of those things? Good question. It's not such an easy task. So there is a lot of tuning which has to be done. And to verify that the trajectories which you're getting from such so low pass filters are actually feasible for your craft. Okay? But we will look at some design methodologies as we go along. Okay. Typically what we do is we want to kind of tune the bandwidth of the model to make a compromise between performance and tracking. So here is where I think I have kind of come up with 3 new terms which you may not be familiar with. So first thing is what is the bandwidth, next thing what is performance, and what is accurate tracking. Maybe that is relatively easy to understand. So let's talk about them first. Can anybody tell me what is meant by bandwidth? How many of you have heard the term bandwidth? Yes, Vallabh, go ahead.
Like range of frequencies or something.
Correct. It is the so-called range of frequencies of your system, which means that in this case, suppose I go back to my so-called low-pass filter, my bandwidth will be 0 to omega c, more or less. That is the region in which I have a significant high output from the system. That is the region which it allows whatever is coming as an input, it is allowed into the system. Anything coming beyond that is not allowed. So my bandwidth of operation is omega c, radians per second. But there is a more precise definition for obtaining the value of bandwidth. Bandwidth is not simply me choosing some random value of omega c and saying that, okay, from here it is tapering off, Let me just choose that value. So it's not an eyeballed value, but there is actually a mathematical sense to the bandwidth. And we'll cover that as we go along. We'll talk about what is that precise mathematical definition which defines the bandwidth of a system. Okay, but please understand that it relates something to how much is the range of frequencies which are allowed for the system in some sense. And that range of frequencies is something which you can tune. And when we tune that, what happens? Either we are doing accurate tracking or we are doing high performance. When we have a very high bandwidth, what does that mean? When I have a very high bandwidth for a filter, what would that mean?
Maybe high frequency inputs are also given to the model.
Correct. So even any of the higher frequency stuff which is being provided, it will try to compensate for that, right? It will try to take them into account and will try to make the desired trajectory track those higher frequency inputs, which means it is trying to give us a higher performance. But then that will lead to a poor tracking because of the inertia of our vessel. We'll actually not be able to track that high frequency responses. Right? Suppose I wanted my ship to do this. It's very difficult to make it do that, right? Because of the huge inertia of the system, it's very, very hard to make it happen. So I have to make a choice. Do I really want that? Or can I pass the filter through a low frequency filter where it's just staying in one place? Right? So these are the things which you have to kind of balance as a control engineer. We have to balance between the performance and the accurate tracking. So you have to make a compromise between them, and that compromise you typically do by tuning the so-called bandwidth of the filter. Okay, so tuning that bandwidth of the filter is quite required as a control engineer, and that's where your so-called, as I said, trial and error part comes in. You try to adjust and see whether that is reasonable enough or it's not reasonable enough, and you try to tune it a little bit more. Okay. Typically what happens is, one interesting thing which comes about is that when we are looking at these choice of filters, one might wonder, how do I choose that so-called filter? How sharp should it be, or how fastly should it respond? And typically what we would say is, why not we choose a reference model that is motivated by a spring mass damper system, in which sense it makes it easy for us to physically understand what is going on. So we can take a spring mass damper system as that so-called low pass filter and then try to tune its parameters, because now we have a more intuitive sense to what is mass, what is damping, what is stiffness. We know what those things physically mean. But although they don't really play effect physically here, at least I can think in these terms and try to tune my bandwidth, rather than trying to tune my bandwidth arbitrarily. So what we will do in the coming lecture is we'll look at so-called velocity reference model, where the idea is that the desired velocity of the craft is tracked as a low-pass filter with respect to the so-called joystick inputs that you're given. Okay, and these inputs, they get translated into that so-called velocities using a so-called second order filter, and you see here that it is representing a spring mass damper system which you have seen before, right? Especially the bottom part of the transfer function should look somewhat familiar when you look at transfer functions and Laplace transforms. Okay, what we are going to do is we are going to stop now, and we are going to come back on Thursday and continue from there on, just to see how these velocity models and acceleration models or position reference models can be generated using these low pass filters. Okay, let me stop sharing here. Any questions before I stop recording?
Sir, could you tell once again why that spring mass and damper is used as a reference model?
Yeah, because it is easy for us to understand, Aditya. It's as simple as that. I need to design a low pass filter. You know that for a spring mass system, how does the RAO look like? We have seen it before, right? So a typical RAO plot of a spring mass damper system will look something like that, isn't it? Where this is the
Yes.
natural frequency, and then there is a rise up because of the resonance, and this is the stiffness dominated region. This is the damping dominated region, and this is the inertia dominated region.
Yes.
So you can see that it's already acting like a filter. It doesn't allow everything what comes in, but it kind of says that between
Okay.
this region to this region is what I'll allow, the rest of it not so much, right?
Yes.
So it's kind of acting as a filter of sorts. So we can then tune it. It's more intuitive to tune it with a spring mass damper system and try to figure out how much bandwidth I want.
Tuning this means finding out the values of the appropriate mass and that
Correct. So or I can either call it in terms of mass, damping, and stiffness, or I might call it in terms of natural frequency,
natural frequency. Yeah.
damping ratio, things
Yes.
like that. Okay.
Okay.
Based on which I can kind of adjust how it actually looks like.
Okay. Yes.
Okay. All right. So any other queries? Yes.
So you asked us to find the diameter of the path rates last week.
Yes. That I'll talk in just a bit. Anything related to the lecture today? Other queries?
So in this spring mass dam system, the input will be actually the force, that the external force that will be given to the model, and the output will be the motion of the
No, usually it will be the input will not be a force. The input will be a so-called joystick inputs or keyboard inputs or whatever control signal which you're giving as an input to the system.
Yeah, actually, I meant as like when you're considering a spring mass dampener system, like that case, the like when you're like looking at that model, the force would be the input, right? That
Yes. In that sense, you are correct that you're looking at it as an input. Yes. So you would be giving the force as the input, and you'll be taking displacement as the output of sorts.
yeah.
Right? Okay. Yeah, that would be right. Okay, let me stop recording here.